So this is lecture number 12, supplementary material. Towards the end of lecture number 12, we were talking about a conical pendulum problem. So we'll continue our discussion on that. So in this problem, the first step was to find the angle alpha. So let's draw the pendulum again. So there's a bob of mass m that hangs with a rod L, which is massless, and this whole system is rotating about the z axis with an angular velocity omega. So the first part was given omega and L. We were supposed to find the angle alpha that the mass takes, that the rod takes for a solution. So we found out that for a very small omega values, what we see is that it will not have any alpha. So if so for part A, we found that if omega was less than square root g by L, then we found that alpha was equal to 0. So the bob simply rotates without the rod making an angle alpha, and if omega was greater than square root g by L, so it was large enough omega, then the solution was that cos alpha is equal to g upon omega squared L. Yeah, this is something we found out last time. So the next part of this problem is to find the angular momentum L about two different points. So we have 2 points. One is point A. So point A basically point A is the center in the plane in which the bob M moves. So the distance from the mass m to the center A in the plane of movement is r. So we can easily see that L sin alpha is equal to r. So given L and alpha, we can find the radius r. And then the other point around which we are interested to find the angular momentum is point B. So if we to find LA and LB, and then we have to figure out, so let's say find and see that they are different. Okay. So the whole motivation behind this part is to see that if we take different points around which angular momentum is taken, then the values are different. So the choice of the point around which we want to calculate the angular momentum has an effect. And the second part of part B is to show that the relation tau about any fixed point O, that is torque, is equal to the rate of change of angular momentum about that fixed point. So for both cases, for both A and B. So this is part B of the problem. Right, so let's start with this part B. So let's find out LA first. We need the figure for this. So the definition of LA says that this is the vector from point A to the mass m. So that is, let's say, our vector r cross the angular momentum, the linear momentum p. So this is m times the velocity v of the mass m. So in this case I am taking r because since we are taking the angular momentum about point A, so we have to take the vector r. This is the vector r. So what we'll do is we'll use r theta coordinates. So one of the coordinates we have is z that I marked. So let's use red color for that. So this is our z direction, so z hat direction, and then we need two more coordinates for this three-dimensional problem. So one is we can take this r hat, which of course changes with time as the bob rotates, and the other one is perpendicular to r hat, which is theta hat, which is tangent to the direction of displacement in this case. So this allows us to write the vectors in terms of unit vectors r hat, theta hat and z hat. Let me draw a theta hat again, it's not very clear. So if you were looking at this from a different angle, so if I had drawn this, so if you could show that this was the direction of velocity and the center was somewhere here, so we could see that r hat would look like this and theta hat, which is the same as the direction of v, so theta hat would look like this. And z, remember, is this direction. In this case our r hat cross theta hat is equal to z hat. Right, so let's write this. So r vector in this case becomes r magnitude times r hat, and the velocity vector we know has a direction of theta hat, and the magnitude in this case, because in this case the alpha angle is fixed for a given omega, so that means that r dot part is 0, so the velocity vector v only has a theta hat component, which is given as r times omega. So this becomes m r square omega times z hat. So that is our angular momentum L about the point A. So what we see here is that the angular momentum in terms of its magnitude is constant, it does not change with time. So because mass m, the distance r from A and omega all are fixed once you fix omega and the length L, and z hat also does not change with time. The way z hat vector is defined, it's always pointing up, so it also remains. So we can say that LA is constant both in magnitude and direction. Next we have to find LB. So B was this point, that is the point at which the rod is hinged. So for this case we'll again use the ideas of vector. So in this case the vector L is, so we'll call L as the vector from the point B to the bob. So it's L vector cross with the momentum, which is still mv. So now with r hat, theta hat and z hat, we can write L hat, the vector L as a component in the z hat direction and a component in the r hat direction. and the velocity v is the same. So m r omega theta hat. So you can see that using these polar coordinates can make our lives quite easy, that we don't have to imagine the directions and do cross products. We can simply use analytical expressions. So the first part is the vector z hat cross theta hat. So the way we have defined r theta and z, z cross theta becomes r hat with a negative sign, sorry, minus r hat. So this becomes L cos alpha m r omega with an r hat. So negative sign gets cancelled. And the next one is r hat time cross theta hat. So that gives us a z hat component. Right. So this is angular momentum about point B. So we can see that the magnitude of this is simply L m r omega, which is constant, but the direction of LB is not constant. So direction is simply a unit vector in the direction of L vector. So this is simply cos alpha, whatever's in the parentheses here. Incidentally, this was a unit vector in the brackets. So you can see that the magnitude of this LB hat is 1. So this is this changes with time. So it's only this r hat that changes with time. Otherwise, the angle alpha is not changing with time because omega is constant, and z hat also remains the same with time. So it's only r hat that changes with time, but that affects the overall LB vector. And if I was to visualize this, so let's try to visualize the direction. We'll have to draw the figure again. Right. So this LB was vector L cross MV. So if we visualize these directions, so this the vector L actually comes out to be in this direction. Similarly, when the bob reaches the other end, that is, let's use a dash line here. So dashed is used to denote the other end. In that case, LB looks like this. These are extreme positions for the bob. So we can see that the vector LB is changing, and the easiest way to see that change is to draw all this LB at the same point, because it's a vector, so we can draw it starting from any point. So let's draw it from the point B, that is easier. So in one case it looks like this, In the other case it looks like this. And if you were to draw a surface which contains the complete LB, so that surface becomes a cone. So this LB, the vector angular momentum about B, forms a cone. So it is changing with time. Okay. So this was the next part, and then we move on to checking or seeing that the dynamical relation which links the torque, let's say first is torque about point A, with the rate of change of angular momentum about the same point. So we have to check this for both points A and B. So let's do that. Now for the case A, we already knew that LA, the vector LA, was constant both in magnitude and direction. So the whole vector was a constant. So that means d by dt of that vector is 0. So that is the right hand side. So let's check the left hand side. So what is the torque about point A? So let's draw the figure again. So if I draw the free body diagram of the bob, it has mg acting in the negative z direction. It has tension from the rod acting in this direction. Now since there is no acceleration in the z direction, so we know that T cos alpha is equal to mg, and the only unbalanced force that is left is T sin alpha, and the direction is towards the center A, and that is minus r hat. So the only unbalanced force left on this bob is the force T sin alpha with the minus r hat direction. So since we are finding the torque, so if I draw the path of this bob, so it's simply the vector r, which is r times r hat, crossed with this minus t sin alpha r hat, and we can see that they are both in the same direction, so this becomes 0. So we can see that this equation is satisfied. So let's look at the second part, which is tau b equals d by dt of LB. So let's note our expression for LB. We'll have to go up. So LB had a magnitude Lm r omega and a direction cos alpha sin alpha. So let's expand this. So we can see that well, the magnitude L, M, R and omega are all constant, because omega is given to be a constant. So we saw that it's only this r hat that changes with time. So this gets simplified to L, M, R omega cos alpha and then d by dt of r hat. This z hat term is 0 because sin alpha z hat does not change with time. And dr hat by dt, if you recall, was omega times theta hat. This is what we learned in the beginning of this course in kinematics of polar coordinates. So this becomes Lm omega square r times cos alpha in the theta hat direction. So that is the direction of time rate change of the angular momentum Lb. Sorry, I missed the vector sign. And since we already know that see omega is given to us, L is given to us, and alpha is something we found out as a function of omega and L, but that function is known, so we can keep that in this expression. So r is actually dependent on L, so we'll have to get rid of r in terms of L and alpha. So let's write that. So we know that L times sine alpha is r, so I can write r as L sine alpha. So this is my expression for the rate of change of Lb vector. So if needed, I can substitute alpha in terms of omega and L, but for now I'll just keep it this way. So now this is RHS. Let's check the LHS, that is tau b, this term. So tau b is the vector L cross the force that was minus T sine alpha r hat. That's the only unbalanced force, that's the only net force acting on the bob. And L, if you remember, L can be written as L cos alpha in the minus z hat direction and L sine alpha in the r hat direction. So again it's only z hat cross r hat that gives us something useful, because r hat cross r hat is a 0. So this becomes L T cos alpha sine alpha, and then we have a z cross r. So if you look at directions, this is z hat, r hat looks something like this, and theta hat like this. So a z cross r will give us a theta hat. Okay, so this is our expression for torque, and since it has a t in it, so we'll have to replace t in terms of something else, and this can be done because we had T cos alpha is equal to mg, so T becomes mg by cos alpha. Right, and what we see is we can use the relation. When we found the angle alpha, we found cos alpha was equal to g upon omega squared L. So if we use that, so basically we can get rid of g. So we can write Lm, and g can be written as omega squared L times cos alpha, and then we have a sine alpha theta. So this becomes L squared m omega squared cos alpha sine alpha theta, and we'll want to compare this with the expression we had obtained on the right hand side. So this was L squared m omega squared sine alpha cos alpha theta hat. It is exactly the same as what we've got now, L squared m omega squared cos alpha sine alpha theta. Okay, so this is equal to RHS. So that shows the fact that the dynamical relation, that torque is equal to d by dt of the angular momentum about the same points, is true. So this was an exercise for you to see that the choice of the point of application, or the point around which you find the torque and angular momentum, is important. And you can also see that in certain cases the expression for angular momentum is much simpler than the other cases. So LA was simply constant in terms of both magnitude and direction, whereas LB was a bit complicated but not that difficult to find. Now this was all done mathematically using analytical ideas, but I will still want you to visualize the situation. So we had drawn this visualization of LB, that is moving in a cone. So from this I would want you to see what is the direction of d by dt of LB vector. So we've shown that it forms a cone, so you should be able to see that when you take the time derivative of LB, that should give you a vector in the theta hat direction, as we have seen mathematically. Okay. So we'll stop this recording now. Thank you.